Okay, I think we are ready to go. All right, so this is sort of the last, I think, of the major topics that we're going to be talking about today. We'll talk a little bit later about how we can do exam prep, just sort of in closing. But this is sort of the last of the topics of the course, and one of the ones that's caused, I think, the most confusion, sorting and searching. So I have here a selection of sorts which we're just going to quickly talk about. I've cribbed these. Let's see if this works. Marvelous, it does, but I don't have any audio. I also love computers. I love it when they go so wonderfully wrong. Output that way, please. Yes, it does. Fantastic. Computers are really awful, honestly. Okay, so with the glorious backdrop of this horrid noise, let's talk about putting things in order. This here is a very slow illustration of one of my least favorite sorting algorithms. This is called the bubble sort, and it's slowly getting faster as we go. But the bubble sort is what I would consider a really awful, slow, very bad, not good sort, because for the most part it has to look at everything multiple times, lots and lots of multiple times. In fact, if I have some arbitrary number n of items here, I've got to look at every single one of those items, well, n times, and then n minus 1 times, because one of those is now going to be in order, and then n minus 2 times, because that's now going to be in order, and then n minus 3 times, because that's now going to be in order. You'll notice as we've been watching, that top section of this list here has been our ordered section. And a lot of these sorting algorithms tend to work by producing a sorted section and then just sort of ignoring that and leaving that to do its thing. The bubble sort is a particularly strange one. It takes the largest element it finds effectively, bubbles it up to the top by pairwise comparing adjacent elements. So we take a pair of elements here, we compare them. If one is greater, then we swap that, or we ensure that is in the larger position of the two, and we move forward. And it's a really simple, naive sorting algorithm as it works its way along. So this is going to do, if you look at the comparison counts up there, we're going to do lots and lots of comparisons for some number of elements. I actually don't off the top of my head know how many elements there are here. But there they are. We will do something like a quadratic number of comparisons. There will be roughly, for n items, something like n squared operations we have to do. N squared comparisons, n squared swaps, at worst. And in following courses like COMP1511, especially when we go into a lot more detail about how bubble sort works, the ordering principles and so on that are behind it, we look at why that's the case. There's a really beautiful little expansion that uses factorial in a most peculiar way. But there it is. That is bubble sort. It's probably stable, probably adaptive. So we use these words stable and adaptive. We have here, by the way, these O followed by a thing indicates the complexity. And that again, I'll just sort of leave that as sort of a thing that is there, it is out there. When you're implementing and working with large algorithms, need to be aware of complexity. But for the most part, you don't really have to worry too much about complexity. Again, 2521 goes into a lot more depth on it. But things to look for, ON is linear time. ON squared is quadratic time. There's a whole range of other ones here. We'll see another one in a moment. But effectively, you want to be erring towards things that, for a certain number of inputs, don't sort of explode. So if I take 10 items, I would much prefer, well, those 10 items to already be in order when I bubble sort them, which kind of defeats the purpose, because the bubble sort's going to always run relative to those number of items in effectively linear, quote-unquote, linear time. But on average, it's going to have to run probably somewhere up to 100 comparisons. When we're looking at 100 items, now we're looking at 10,000. When we're looking at 1,000 items, now we're looking at 1,000,000. And you see why bubble sort isn't particularly wonderful. I don't like bubble sort especially, but it works. It's a really naive, simple sort. It works. Another thing to mention is that it is probably stable. That is, it retains the order. Most implementations of sorting algorithms don't just deal with sorting numbers. Yeah? As we saw with linked lists earlier, yes, we could just have a linked list of integers, but that's not particularly interesting. More interesting is if we have linked lists of complicated things, like whale sightings, for example, or database records, or iTunes library records, or whatever. So stability is, if I do a sort by some property, and then this is something you would have seen. If I sort by one property in something like iTunes or similar, and then I sort by another property, I'm not going to entirely blow away the sort order. There will be some order that is preserved when I sort by title, or sort by artist, then I sort by album. There will be relative order preserved. And that is what stability talks about. Stability talks about whether the sort will preserve relative order. Bubble sort usually does. It's possible to write it such that it doesn't, but it's usually stable. It's also usually adaptive in as much as it's not going to, as we saw, it goes up the list, but it doesn't deal with those already sorted items at the end. Again, you could write it so that it does, but there will be a sorted section that is produced, and you don't have to resort the sorted section. It's sorted, it's in order. And that is what we mean here by adaptive. Bubble sort naively, it's awful. It's gonna be really miserable and sad. 2521 again goes into a lot more details about why bubble sort makes us all sad. Here's a different sort. This is a completely different type of sort. Bubble sort does pairwise swapping of items, but there's a whole different family of algorithms, these divide and conquer algorithms. And what they do is they take the problem and they split it up. They make it smaller problems, lots of smaller problems. In this case, quicksort, and there's another one, merge sort. I love merge sort. Quicksort and merge sort tend to just halve the problem set effectively, or do something very close to halving the problem set. So here we have three different, there are actually quite a few variants of quicksort. They're all called quicksort, but there are a few variants of it. And they're basically, they all, well, pivot on, where the pivot is. By pivot, yes, it's a pun. Yes, it is. What we mean by pivot when we're talking about quicksort is we pick a value and then we produce two collections of values. One collection where the values are all strictly less than, one collection where the values are all strictly greater than our pivot, and then we just sort those and they're now in order. Magic, recursion all the way down. Let's have a look at what that looks like to run. Again, this is usually stable, this is usually adaptive. It's a lot more discordant as it's going through. Let me just pop that back to the beginning so you can see. We've chosen a pivot here in the middle. And now we've shuffled all the values on either side. What we're doing here is we're partitioning our list. And you can see we're sort of making passes through the list to sort it in small pieces. And those small pieces are easier to sort, it turns out, if we choose them right. Hooray! the hooray is required. Quicksort, as we saw, tends to split the problem space by pushing values that are high to one side, pushing values that are low to the other side. However, quicksort is really easy to break. And you'll notice here, like we saw with bubble sort, we're talking about order n squared, this O(n) squared thing. And we said, yes, we don't like that. We want to avoid that. And we see here that quicksort, this first quicksort up here, max quicksort, which chooses the last element always and does a quicksort on that, with that as the pivot. That is always going to go horribly, horribly wrong if the list is in order. Because, or in reverse order as well, because it will always just have to resort the entire list. Many sorts fall over if you give them already sorted data or nearly sorted data. Some sorts work really, really well when you give them nearly sorted data. But it's fairly common for a sort to just completely freak out when you give it in-order data. Quicksort, the naive quicksort which picks the largest index of the array and uses that as a pivot, that is a particularly bad one. These other ones here do significantly better. There's a magic goal with sorting algorithms that has been proven to be you can't go faster than this, and it's n log n. That is, for n items, I need to ask sort of on the order of half of those items to move. And sort of the n log n sort of represents that weird questiony thing. There, again, is more depth than that in 2521. I'm just going to say that's a thing. N log n is the best you can do with a sort. So it's all very well to say, yes, look, sorting algorithms, wow. COMP1511, as I keep on saying, goes into incredible depth about how those algorithms work, about putting data in order. So what we're going to do is we're just sort of going to, well, cheat a little here. Let me lose these lights because this, I can barely read that. There we go. We have in the standard library a selection of really fun, wonderful functions. Here is one of my absolute favorite of these wonderful functions. It's called qsort. It is not a quicksort. It's actually not specified what sort of sort this is. It might be a quicksort. It might be a bubble sort. We don't know. It's not specified. On Linux systems, such as those on CSE, it's actually a apparently quicker sort. I have no idea. So let's have a look at how we'd actually go about using that. Let me... yeah, here we are. Whoops. There we go. So I have here a selection of strings. These are... I can bring some light back, because now I can actually see things, can't I? Lovely. Right. Here's a selection of strings which... Better. Here's a selection of strings. Man, I wish I had syntax highlighting. I miss syntax highlighting. Here's a selection of strings which are not in order. Or, depending on how you look at it, they are in order, because these are actually track titles from an album which I just pulled randomly out of my music collection. And I actually think it's a very good album. I highly recommend it. Anyway, these aren't in order, obviously. I have here a little bit of code that just prints these out. And there they are in order. Quote-unquote order. Make here... Again, make just recompiles something if it's not up to date. So in this case, if I were to change the source file, order.c, it would recompile that for me. In this case, it hasn't changed, so hooray, I can just do it. Or if I was feeling really lazy, I would do dcc-o ord.c. But again, lots of typing, lots of effort, I'm lazy. So there is our track listing in track order. What if we want alphabetical order? So what I can do is I can actually do a sort on this using qsort. Qsort takes, whoopsie daisies, qsort takes 4 arguments. And these 4 arguments are, in order, the base. This is a pointer to the first item, effectively. Then we have the number of items, amazingly. Then we have the size of each item, and then we have this compare thing. And I'll come back to that in a moment. But this function just takes that data, sorts it. So if I've now, this quicksort's now going to run. So if I just put a new line there, just to split our output up, and let's just compile that. You'll notice that one of these is in order by track, but one of these is in order alphabetically. Yes? And I'm just using strcmp, actually, to compare pairs of values. So up here, I have a prototype for this function compare. And what we do is we just pass in that function. This is a really strange thing. We just pass in a function. And this function has a really scary looking invocation and is really quite bizarre. And effectively, you just pull this straight out of the manual because the manual has this code in it. You just go man qsort and it will tell you. Not kidding, it actually has right down here. Effectively just this code, you just grab it out of the manual and it just works. What we have here, what is passed to this comparison function is pairs of values. And this comparison can be arbitrarily complex. I could be comparing database records, I could be comparing really like hairy things, structures of data and so on. In this case, nice and simple, it is just a set of strings. And it gives us a pointer to each item. It gives us a pointer to each item as a void pointer, but then it turns it back into, or we'd have to turn it back into a char pointer. But it's not actually a char pointer, it's a char pointer pointer, which is a bit peculiar. It's a pointer to each of those strings. Each of those strings which we then dereference, string compare, and it just sorts. It's lovely. Yes?
A lot of the time I see for qsort, for the number of items, they do number of items minus 5.
No, I haven't ever seen that. Yeah, right. So what this is doing is it takes the list of arguments that are passed into this program and it sorts them. And it doesn't want to deal with the first parameter, the first of the things in argv. What are the things in argv? We've talked about this before. What is in argv? Argv is an array of strings. What are those strings? Let's digress briefly. Let's just print those out. Muscle memory on automatic right there. Okay, I'm going to print out all of these arguments. Once again, I'm not sure what's going on there, but anyway, there we go. We're going to just print out each of the arguments in turn. And the way we're going to do that, I'm going to use the for loop because I'm a lazy old bastard. For int I is, well, let's start at 0 and let's work our way up. Well, I is 0 until we've reached the number of arguments there are. argc, of course, is the number of arguments there are. argv is a pointer to the first argument. And I++. And we're just going to print out the argument number, and I'll just print out the string. argv at I. So this is just going to loop over each of the things in argv and print it out. Well, that's not very interesting. There's a...
What does the percent thing do?
Hmm?
Like, you know how you said make argv, like,
Oh yeah, the percent there is because the program has ended before the end of file. It's my shell telling me that there's no new line after the program exited there. So in practice, it's just $v. Let me give this some more arguments. And it prints those out in order. I'm sure these projectors are going weird, because I'm sure these were brighter earlier. Anyway, there they are. There's our arguments. In order. So each of the words, quote unquote words, that we have in our program represents one of the arguments that is passed to this program. We get those arguments, and they come down through argv. All right? So the reason in this man page we refer to that particular part of the argument string is because we don't want to sort the name of the program. The name of the program, or the name the program was invoked as, is always the 0th thing in the argument list. All right? So we have here our array. We have the number of items in this array. The way I take the number of items is by saying, well, this is a trick that only works when the array is in this function, in this stack frame, actually, which is I can take the size of the array. This only, and I stress, only works if I'm in this stack frame.
so can you repeat the part of the stack?
Yeah. If I were to pass this array into a function, this trick will no longer work. Because the array turns into a pointer. Size of will give me the size of an array if the array is in scope. If there's a reference in scope, if I've passed it, for example, then it will just turn into a reference, and this trick doesn't work.
Wait, you said an array turns into a pointer?
Yes, arrays and pointers are interchangeable. In this case, the array, I can actually talk about the array's elements in this function. This is a very strange trick that relies on that being there. This is extremely weird. But if I'm in the same function that array was declared in, I can see how big the array is. It's very weird. And again, this, as I keep saying, this trick won't work if I am not in this function. And, well, it gives me the size of this array, but it gives me the size of this array in bytes. The number of bytes that are used to store this array. But I'm interested in the number of things there are in this array, and the way I find that out is by saying, how big is one of those things in this array? And I divide. And I wind up with the number of items. Because I know how big one item is. I know how big all of the things are. So this gives me the number of items there are of that size. All right? So that is a really strange little trick. And this, of course, just sort of works. One thing that is really peculiar about C, and again we'll talk a bit more about in 1521 and 2521, is that I can pass functions as arguments to programs. It's very strange, very weird, and sort of a bit, just assume it works for the moment. In future courses we go into more detail about why it works, what we can do with it, etc. All right? So that is how we sort of cheat the sort, which is we just use someone else's sort. We're interested in solving problems. And under most circumstances, when we're trying to solve a problem, we don't really care about all of the heavy lifting that we have to do along the way. We just, do it. Use a sort. You'll basically never have to implement things like a sort or a search or a linked list even after this course. 2521, of course, you'll have to implement your own sorts. You can't just use this trick, but for the most part, you can rely on libraries. Library functions exist in basically all languages that you will ever work with to do stuff like sorting and searching, but if they don't, you can write them. So let's change TAC entirely, unless there are any questions on that. You.
Sorry, could you do the compare function thing again? Like, do you just have, like, because I know it works for like character strings, but like in the exam, how would we do it for like ints or something?
Yep, okay. So let's say, let me grab this. Let's turn this into an array of integers. I have an array of integers up my sleeve right here. Here they are. Cool. So here is some list of items, and I'm going to sort them. For this, I'm going to need to write a new comparison function, but we'll do that in a moment. I'll just fix up these things here. Each item is no longer a char star. Make sure you get these things of the right type, otherwise you're going to have a bad time. So we're going to sort this array of things. Qsort sorts in place. The array after Qsort will be in order. If you want to keep the original array, that's your responsibility. You need to work out how to keep a copy of that. And let's print these out before and after. Cool. Our sorting function now, once again, it's the same shape, effectively. Let me turn that off so I've got some color. So it's again the same shape. It's going to take a pair of pointers, a pair of void pointers. These void pointers point at the items in the array. So what I'm going to need to do is dereference them. The problem is that to dereference these void pointers, well, I need a value of type void. Such a thing doesn't exist. Void is explicitly the type for values that there aren't. Void is the type for values where there are no values. Void has no values. So dereferencing void star would say that I have a value of type void. That doesn't make sense, so we have to turn this into a type which makes more sense. In this case, we know we're sorting an array of integers, so I will cast A, and this is whinging because I don't have a semicolon there, and it's going to continue whinging. I take A, which is a void pointer, I turn it into an integer pointer, and I dereference that, and that gives me an integer. And now I'm going to need to compare that to the other thing, which is, of course, another integer star, B. And let's just return the difference. The brackets here do what is called typecasting. This is something that you'll basically never need to do except when you're writing functions like this. Some people will say, oh, yes, every time you allocate, you must typecast. No, you don't. Void star, well, int star x's is int star malloc. You will see stuff like this. You don't need to cast here because the compiler knows how to turn that type into the other type. Blah. But for this type here, you do actually have to do that cast. So I need to turn my A, which is of type void star, into something that I can dereference, i.e. type int star. And I'll call it a underscore because I'm really bad at naming things. And again, I'd need to do that with B. All right, and it's whinging here because I'm not using them, but that would be how you do it. This takes a thing of one value and it turns it into, or thing of one type, excuse me, and turns it into a thing of another type. That is what these parentheses with a type name in them do. And again, you'll basically never have to do a typecast ever. This is basically the only place I can think of where you would need to do a typecast. Other places you will need to do it include COMP1511, where you actually go spelunking into how the types themselves work. and you sort of have to go, this type is actually a different type. Sometimes you will see this done to do division tricks. So if I have an integer and another integer and I want to divide them and I don't want the answer to be 0, then I cast something to double and then I'll get a fractional answer. Yes, cool, or multiply by 1.0. Anyway, so there is this nice simple comparison function. The comparison function needs to return 0 if the values are equal. Needs to return a value less than 0 if A is less than B, and a value greater than 0 if A is greater than B. And that works precisely how we would expect. In fact, this would be how the last line effectively of stircomp looks. It takes one character and another character, takes the difference. Nice and easy trick. And just to prove this works, there they are. So here is my unsorted data coming in, and here's my sorted data coming out in, amazingly, sorted order. All right? So about the only trick to remember with qsort is the order of arguments, which you can find in the manual, and what each of the arguments means, which again you can find in the manual, and how to build this comparison function. The comparison function takes a pair of pointers into your array, and you have to come up with their order. All right? Arrays of structures, easy. Dereference things in the structure to work out what the order is. Okay. Let's quickly talk about something subtly different, but also very similar, which is, here is a list of values. Here's the same list of values, in fact, that I just had before. How do I find something in this list of values? Let's say I'm looking for the value 9. I want to know if 9 is in this list. How do I find it? I mean, yes, there it is. It's right there. Yes, but how do I find it? Because this list isn't in order, I don't have a choice. I have to walk along this list, item by item, checking. And this is what we call a linear search. And a linear search works by, well, you just have to walk over every single item. So let's do that. This function takes a command line argument, which is the name or the number to search for, and it turns it into a number there with A to I. And now we just have to walk over our list. Here it is. Come on. There we go. There's our list up there. Computers are absolutely the worst. There we go. So I need to look through this list of items. Again, I start with the first value until I reach the size of that array. N items is a little trick which just grabs that size of divided by size of trick that I had earlier. And now what I'm going to do is I'm just going to look through here to see if I found the value. What I need to do is I need to look at each single value. So I've got to say if xs at I is the value we're looking for, then and we'll exit. Otherwise, we didn't find it. And I'll need a semicolon there. And let's return 1 to make it obvious that something went wrong. All right. So what we're doing is we're going through each item in turn. And this is terrible. The reason this is terrible is that every single item is an item that I have to look at. Okay, I sort of cheat a bit by stopping when I've found a value, but effectively, at worst, again, order n. I have to look through every single item that I have. That's terrible. I hate it. But it works. I'm going to need to give it a number. Or, of course, it will crash. That works too. Let's give it 3. Let's try the correct argc. Oh yeah, that printf is missing a thing, isn't it? Don't forget, this is a really, really important thing. And this is something that Curtis talked about in one of the lectures earlier in the session. But this is something really, really important to remember, which is that printf is extremely dangerous. Printf, if you forget to give it things like arguments, will just happily read its way down the stack. It will read its way down through your stack frame looking at values, and usually that's not what you're looking for. The only way you can determine that's happening is pretty much, or the only way you can guarantee, you are guaranteed to be able to find that is happening is at runtime. Compilers these days can tell you, but it used to be that compilers couldn't tell you. Compilers didn't know how to read printf format strings. Now they do, which is pretty terrible. Okay. This is whinging because I'm comparing values of different type. That's fine. Else search now actually doesn't crash. But if I say I'm looking for 2, I say, well, I found it at 4. Whoops. And what value are we looking for? 2. That is index 4. That works quite well. If we're looking for or for 9, excuse me, that'll be at index 5, etc., etc. If I'm looking for a value that is not in this list, it won't find it. Amazing. Here's an interesting question. What is wrong with this code? Why mightn't I like this? So there's 2 reasons that I don't like this code. One of the reasons is, well, I have to look through every single item. What is a reason that might be bad about this code? What is something that might be bad about this code? And this is a nice little subtle thing, but this is something that's very well worthwhile thinking about. I mean, we catch the case of if we didn't find something. But to tell you that I didn't find something, I've had to look through every single item, yes? To tell you that I did find something, I'm going to have stopped at some point in the middle there. Let's say it takes me, I don't know, I've got a really slow computer. It takes me a second to check every single thing. If it takes me 10 seconds to run this program, I don't even need to see the output to know for these 10 inputs, I didn't find the thing. But if the program finishes faster than in those 10 seconds, then I found it, yes? I don't even need to see the output. I know it's found that answer. And this is actually an interesting little bug that if you are going on to do something like COMP1511, you might find interesting to think about. Sorry, I'm just looking intently at a COMP1511 tutor who's looking a little bit dazed and confused. All right. So, linear search is okay, but we can do better. And the trick to doing better is, well, what if these things are in order? I'm looking for the number 9. Once again, how do I find it? Knowing that this list is in order. Yes. Yes, I could just jump straight to the 8th index. Let's say, though, that I know it's in order, but I don't necessarily know that the 9 is there. So it's an ordered sequence of numbers, but I don't necessarily know that they're all there. How do I find that 9? Well, one approach might be to look halfway along the list. I know how long the list is. I know how long the array is because I have to know how long the array is. Otherwise, I don't know how long the array is. Either I know or that information is lost to me. I'm given that information in this case because there are 10 items in the list, and I've explicitly said that. Otherwise, I don't know. let's say I look halfway along the list at, say, index, this list has 10 things in it, so let's look at index 4. At index 4, I find the value 0, 1, 2, 3, 4. I find the value 5. Yes? The value I'm looking for, 9. Is that greater than 5? Amazing, it is. So I know that it's not going to be less than that, fairly obviously. So I only need to now look at the values from index 4 up to index 9. And so let's say I look at index 7, halfway between the place I know the bottom bound of it is. I know it's not going to be in this portion down here. Let me move some cursors around. So I'm looking for 9 up here. I look at, say, index 5. I now don't really need to look at any of these values ever again if I'm looking for 9. Because there is order, because these values are in order, I don't have to look at those. I only have to look at the other half, these values up here. And so I would look at the middle one of those. Again, I'd look at 8. Is 8 9? No, but it's less than 9. So again, I now don't have to look at some more values. I don't have to look at 6 and 7, because I know those can't possibly be 9. This list is in order. It's not going to suddenly become not in order. So now I have these values, 8 through 10. Actually, really only 9 and 10, because I know it's not 8. I looked at that earlier. And so now I would look at, say, 9, and oh, there it is. If I was doing a linear search here, I would have to look through 1, and then 2, and then 3, and then 4, and then 5, and then 6, and then 7, and then 8, and then 9. I've had to do 9 comparisons. But by doing this trick, a binary search, in as much as we split it in half, and we split it in half, etc., etc., etc. By doing a binary search, we only had to do how many comparisons? Probably somewhere between 3 and 4. Because a binary search only needs to look at log, base 2, the number of items in the list. Implementing a binary search is actually really hard, which is why, once again, we cheat. Here is bsearch, which is also in the standard library. It looks very, very similar to qsort, except for one additional item, which is key, the thing I am looking for. And then I give it the base, the number of things, how big each thing is, and a way to compare the things, and it will give me back a pointer, a void pointer. This thing works on any pointer type, and we can improvise to make pointer types. In this case, it will give us back either null, if it couldn't find anything, or it will give us back a pointer to the thing it found. And again, this does do a binary search. This uses this comparison function which returns equals 0, or less than 0, or greater than 0. It looks at halfway along the list, and then one of the quarters along the list, and then one of the eighths along the list, etc., 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 to find the value. Let's look at what that actually looks like, though. Let's look at a little program here which I have stolen from the documentation. And this function takes a structure which is filled with months. It's a really boring, dull structure. But there it is. And I have here a comparison function, and I've sorted these to make sure they're in order. This is quite important to do. I really, 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 really want this list to be in order, because binary search does not work if the list isn't in order. That's one of the properties of binary search. It is something that has to have ordered input to work. Otherwise, it's just going to produce garbage. In fact, I think it is undefined It produces undefined behavior if the list isn't in order. And then we give it some values. Once again, we give it the thing we are looking for. In this case, we've made a structure and we've put a value that we're looking for into it. And we give it the things we're looking through. We give it months, we give it the number of things, we give it how big each thing is, and we give it a function that knows how to compare two things. And it prints out if it found something, what it found. Here's our comparison function. Once again, it looks very, very similar to the comparison functions we had before. It takes a pair of pointers to void star, which we need to turn into things we can do something useful with. We turn them into struct pointers, and then we just stab them. We stab the field that we are looking for, in this case, the name field. And in this case, I'm looking for, well, it's not going to take a number, it's going to take a word. Let's say we're looking for January or December, and it's just going to do the thing. It does this by looking through that list we had earlier. It's looking through this list. It's going to start out looking at June or so, very probably. Whoops. It's going to start out looking at this item. And it's going to say, well, is this item, let's compare this item with the item we are looking for. And in this case, it's just doing a name comparison, just taking that name field and comparing that. It says if this name field is equal, well, we've found it. If it's less than, then we need to look through the upper half of this array. Otherwise, we have to look through the lower half. Yeah? And so, well, say we're looking for December. Actually, no, let's say we're looking for October. That's more interesting. Once again, we have to look through this list here. We're probably going to look at, October was a bad choice because that's what we're going to look at next. And it's going to look at that and go, oh, that's equal. It's found it. Instead of having to do 12 comparisons, one for every item of this list, we only have to do some of those comparisons. We have to do log the number of items we're looking through. All right? So that's sorting and searching very quickly. Two wonderful sorting algorithms, two wonderful search algorithms, and really just great ways to cheat when you hit a sorting or searching question. Questions? Yes?
So what am I actually expected to know in the exam?
Good question. I would strongly suspect that if you are a student who's doing really, really well, and you're going to come out of this course with a distinction or a high distinction, you're probably going to even higher than a high distinction. Does it go that high?
I mean, like the high end of high.
Okay, the high end of high distinction. You may be required to solve problems that make you sort or search or do something complex. But it won't just be simple bits of data that you're sorting or searching. You will actually have to probably think quite hard about how you're solving that problem. If you're not looking to get the highest of high marks in the course, that's okay as well. Have a crack. QSort and bsearch are probably going to be great secret weapons to have. Know how to read the documentation for them because they will save you immense amounts of time and pain trying to actually build sorting and searching mechanisms. It might be. It might be true that you're restricted to not do those. In which case, things like bubble sort, actually rolling your own bubble sort, it's not that hard. Rolling your own linear search, well, you saw what that looks like. You're just looking through every single item. You don't think of that as being a search algorithm, but it is. It's a really, really simple one, but it's a search algorithm. It will find you a thing that you are looking for. All right? The Awkward Silence of the Lambs. Great movie. Lots of very long, awkward pauses. Yeah. Okay. Any other questions on sorting and searching before I give you a couple of really awesome... Yay.
Is that going to be online too?
Yes, I'll get this code up. And
All of the code and slides today will be made available on WebCMS.
that probably won't happen until afterwards, unfortunately. We were hoping it would happen before, but things did not go to plan. I mean, we had to move lecture theatres at the drop of a hat, so... Yep. And of course, there'll be some notes in there on how you actually read through the documentation as well. Right, I have a handful of really cool tips for exams, unless there are any more questions on sorting and searching. Yes?
Did you say that compare part was in the manual, or was that the...
Yes, yes, you'll be able to see how to build a quick and dirty comparison function.
Is that there?
Yes, right at the very end of the manual entry for qsort and bsearch. Yep. So right down here, there is actually a section called example, which is about 80% of the way through the document. And there it is. Shows you how to actually build a comparison function and how to use it, as well as a whole bunch of how stuff actually works in here. All right? The same with many of these manual pages. And of course, don't forget, you may find some of the stuff in the See Also section is interesting. So here we have, well, it says there's a function called alpha sort somewhere, a function called version sort, and of course our good friend strcmp, as well as a command down there, sort. Any other questions? Okay. Exams. I think all of you by this point have actually been in the prac exam environment at least once. In your labs last week, was it? Something like that. And you would have seen what the prac exam environment looks like, and you would have sort of had some experience of how to program under pressure, but it is hard. It is actually really hard to program under pressure well. One of my absolute best tips for you, if you are going to be programming under pressure, programming even in exams, my absolute number one greatest tip: sit on your hands. That may seem completely and totally bizarre for a programming exam when you probably need your hands, but let me explain why sitting on your hands is probably a good idea. You don't want to sit on your hands for the entire exam, of course. Just for portions of the... If you sit on your hands for the entire exam, what are you doing? You want to sit on your hands because the one thing that I think all of you will fall victim to, and I know I fall victim to it as well when I'm in an exam. I've done a few prac exams at CSE. And the one thing that I always wind up doing, and I'm sure you've done this as well, is just look at the question and go, oh yes, let's just start coding. And you just jump in and start writing code, and everything is on fire after about 5 or 10 minutes, and you don't know why. And you're just sitting there debugging, and this mess of code is getting more and more convoluted. And it's terrible. And the way you get around this is you don't just blindly leap. The first thing you do is you read the question. And the reason I suggest sitting on your hands is to reduce the temptation to just go, ooh, code, yes, good, and just sort of blindly write code from here to the end of time. Don't just start writing code. Stop, read the question. Think about what it is you're setting out to do. Think about how you need to approach the question. Draw diagrams. You'll have working paper available to you. Probably want to bring along a pen or pencil. In fact, you'll most definitely want to bring along a pen or pencil. You'll need to fill in various paperwork about the fact that you have done an exam. Read the question. It is oh so likely to be chock full of really useful information that you want to solve the question. Read the code that is provided to you. The number of times I have seen students just ignore half the code they're provided, blindly just start writing code, and then they've discovered that, oh no, I spent 3/4 of my working time re-implementing a function that I was given. You laugh, but it happens. It has happened so many times that I have counted. I've invigilated a lot of exams, and yeah, it happens. People do it. So, sit on your hands and use your eyes. Read the code. Read the question. Read the material that is provided to you before you blindly leap. All right? It's also a good idea to make sure you've read through all of the questions. We do give you some reading time, I believe, up front. So read through all of the questions and start getting an idea of what you're going to do first. Do some questions that don't just jump for the hardest question and hope to get a whole bunch of marks right at the end, because very probably that's not going to happen. If you just sort of blindly jump for the hardest question, the hardest question usually is not worth all that many marks. Not as many marks as is justified for the amount of effort you're going to put in. Score easy points. Very useful to jump in. Probably the early questions are going to be easier, but that's not guaranteed. One exam paper that I have read recently, the hardest question was the first one, and they were in reverse order of difficulty, and the last question was, and this is for a, what is it, 4th year subject, the last question was reverse a string. And so many people didn't get that question. You guys could reverse a string, I'm sure, if we gave you a string. You don't even have to store it, you just get char of them. Hope for the best. What else? There's a whole bunch of revision questions up now, I believe, on the website. You'll be able to go through some of those. There's some really useful questions in there to give you some good practice with strings and characters. If you are just despairing, I really strongly recommend practicing and trying. Your tutors may be able to help as well. You may be able to reach out to them at some point between now and the exams. Some of them will also be preparing for exams. I know I should be preparing for an exam or 2 or 3. I'm not, but, you know, I should be. Procrastination, yes. I think that's about all of the really interesting things to be aware of on the exam. The exam sets out to give us some idea of how well you do at programming sort of on the spot. But it also gives us a way to spread you out a bit, so we can find the people who are going to pass the course, and, you know, you're not going to do amazingly well, but that's okay. Presumably you may not have had any programming experience before, and you've made it to passing the course from absolute 0. You have won. You have done so very, very well. And some of you, you've come into this course and you'd probably be able to just come out of the final exam with 80, 90%. And you've maybe learned a couple of things and you're going to come out of the exam with 90 or 100%. Yeah, okay, cool, fine, that's fine as well. You've probably not learned all that much out of this course, but it's interesting stuff that you may have picked up along the way. And the exam just lets us spread you out a little bit so we can see who goes into what bucket. And then, yes, your mark falls out the end. It's really all rather undignified how your marking happens. The mark just sort of falls out one end. Right. The shape of the exams, I think 6 or 7 practical questions, somewhere in that ballpark. I don't believe Andrew Taylor was committing to any actual number. Yes, there will be a skeletal exam. But what we mean by skeleton exam is it will be the exam paper. We will give you the exam paper. And you're thinking, what? What? But we've removed all the actually interesting bits about what the questions are. So you'll be writing a question to redacted. In this question, you will be given redacted. And you will need to write a program to redacted. And that will give you some idea of also probably marks that are associated with each of those questions as well. To give you some idea of the shape of how marking will happen for those. It'll give you an idea of how questions are broken up. There may even be some information leaked about the exam in there as well that might be interesting to you, but who knows? There will be a portion of the exam where you don't get you don't get a terminal, you don't get a text editor, you've got to sort of guess. Or if you are doing better than that, you will be sort of working out what a piece of code does or something along those lines. And then there'll be some implementation questions where you actually have to write some code to do a thing. Yeah. So we'll have that skeleton up before the exam, I hope. Curtis is looking particularly pained over there because there have been occasions, I know, where exams have been finished, you know, just before the exam starts. Not for this subject, but certainly for other subjects. Yeah, by how many minutes? Whole minutes. Whoa! Luxury. Yeah. One thing to keep in mind is that sometimes things go wrong in exams. One thing to remember is just don't panic. If things are going wrong in the exam, there's probably a lot of tutors who are running around panicking, trying to fix stuff for you, and Andrew Taylor is probably tearing the remnants of his hair out over trying to fix the exam and make sure everything works. So if things are going wrong, don't panic. Do make sure you let an invigilator know if something is going wrong and you don't think anyone else has noticed, purely because then we will know that something is going wrong. Things like tests being broken, that happens, particularly if you're in a morning session, so just be on the lookout for that. Yes, I think that's about it.
Pretty much it.
Yeah. Yeah. All right. Any questions?
Highly recommend looking at those revision questions.
Yes. Yes, the revision question's up on WebCMS 3. Up here somewhere. I really strongly recommend you have a look at some of these revision questions. There'll be solutions coming out later. They'll be out by Monday, apparently, so hang tight. But definitely have a go at those questions. Don't just learn the answers, because that's not going to gain you anything. Learn what's going on. Practice the skills. I think that's it. Let's wrap it up. Thank you very much for coming along on such a lovely, horrible day outside and coming and sitting with us in the warm and dry. If you've got any questions, don't forget, course forum is still open. People are answering questions. Otherwise, good luck with the exam. Break a leg. We'll see you there. Hey, I'm an actor. I'm going to say break a leg.